We can also do measurements like this at constant pressure. This is easier than doing constant volume. When a chemical reaction occurs that's open to the atmosphere, then it's occurring at constant pressure. But now the energy can evolve as both heat and work, because you can have this pressure, a volume change against pressure. Often we're only interested in the heat exchange. The work is not useful, and so we don't really need to know what that work is. So here's another term we have to introduce here, the enthalpy of a system. So enthalpy has the symbol H. I don't know why. I guess E was already taken. So the enthalpy of a system is the sum of the internal energy and the product of its pressure and volume. So H equals E plus PV. Enthalpy is a state function. It does not depend on how you get there, just where you started and where you ended up. Internal energy, pressure, and volume are also state functions. So we are going to be looking at the enthalpy change, or delta H. The delta H of a reaction is the heat evolved at constant pressure. So H was E plus PV. Delta H is delta E plus P delta V. It's not delta P because the pressure is constant. The change in energy is Q plus W. Q at constant pressure plus W. P delta V, that looks like work. Work is negative P delta V. That's that pressure volume work. So this piece right here is equal to negative W. So QP plus W minus W just ends up being QP. I'm not going to test you on that derivation, but this is what scientists do. It's like math voodoo or something. So delta H is equal to Q, heat at constant pressure. Okay, so I don't really expect you to retain what I'm going to tell you right now, but I need to just tell you anyway. So delta H and delta E, they are very, very similar in concept. They are also often similar in value. The actual number is very similar. But there is a difference between them. Delta E measures all the energy that's exchanged with the surroundings, heat and work. Delta H measures only the heat that's exchanged under conditions of constant pressure. Most of the time, the difference between them is just not significant. And so I pretty much expect Chem 1A students to just treat delta E and delta H as the same thing. Okay? There is a difference, just know that, but we don't really need to care about the difference at this point. The difference becomes more significant when we have reactions that either use or produce large volumes of gas, where you get a big volume change, then the difference becomes more significant. We're not going to deal with anything like this, so we can just kind of mentally equate delta H and delta E. The signs follow the same conventions for both of them, and it's like money and your pocket or your wallet. Money coming in is positive, right? You like it when people give you money? It's a positive experience. Energy or heat coming in is positive. Heat going out is negative. And you have to think about what's your point of reference, right? Because if I give Lauren $5, it's negative 5 for who? It's negative for me, but it's positive for her, right? So the sign depends on what part of this you're looking at. There's always two parties, the system and the surroundings. So most of the time we're looking at the system. So you put yourself in place of the system and you say, well, is the system, am I losing or gaining? And that's how you determine the sign. An endothermic reaction is when heat's coming in. Endo is like into, it's coming in. An exothermic is when heat is exiting. At the exit sign on the door, that means we're going out, right? So heat going out is exothermic. So we mentioned earlier those little heat hand warmers. Iron filings being oxidized from oxygen in the air, and it releases heat and it warms up your hands. That is an exothermic reaction. The reaction is releasing heat into the surroundings. Your hands are the surroundings, and you feel the warmth from that reaction. There are also chemical reactions that do the opposite, and those are used in these instant ice packs. You break a little seal in there, mash it around, get the chemicals to mix, and it gets cold all by itself. It's an endothermic reaction, and it's pulling energy from the surroundings. Those typically contain ammonium nitrate, and when that dissolves in water, it's an endothermic process. It causes it to absorb energy, and so then your hand or whatever, your sore shoulder, gets cold because the heat's going into the reaction. Another example of an exothermic reaction is a flame. So this could be on your stove or your Bunsen burner. It's an exothermic reaction. It's releasing heat into the surroundings. So identify each process as endothermic or exothermic and indicate the sign of delta H. So an ice cube melting. Is the ice cube taking in energy or releasing energy? So we're like, well, I'm not really sure. Well, let's think about what could we do to the ice cube to make it melt faster? Add heat. So if the ice cube is melting, it must be taking heat in, right? So then is delta H positive or negative? Positive. So here delta H is positive, or we'll often say delta H is greater than 0. Okay, nail polish remover quickly evaporating after it's accidentally spilled on your skin. Now, guys, you might not have spilled nail polish remover on your skin, but you've probably gotten an immunization where they rub alcohol on your skin, and what does that feel like? It feels cold. Well, it might burn, but it feels cold also. So here, the process is this chemical evaporating. And so we have to figure out in that evaporating, is the chemical absorbing energy or releasing energy? We can't see what the chemical's doing, but we can feel it by what's happening to our skin. If my skin is getting cold, does that mean my skin is losing energy or gaining energy? It's losing, right? That's why it's getting cold. So if my skin is losing energy, then the nail polish remover must be absorbing it. So is this endothermic or exothermic? It's endothermic. I should have put this up here. That's endothermic. This is also endothermic. And so delta H is positive. Gasoline burning within the cylinder of an automobile engine. Well, that's something we kind of know happens, but most of us don't get into the insides of the engine to actually see it or observe it or anything. But have we experienced things burning other places? And do you know what happens to the temperature of your engine when it runs? It gets hot, right? If you've ever messed around in there, you might have burned yourself. So the engine's getting hot because that gasoline burning is absorbing energy, releasing energy, right? Pretty much any combustion reaction, combustion or burning, is going to be releasing energy. Doesn't really matter if it's gasoline or natural gas or butane. So this is going to be exothermic, and that means that delta H is going to be less than 0. Because from the standpoint of the gasoline reaction with oxygen, that is losing energy. it's positive for the surroundings. They're gaining energy. Any questions? The signs can be confusing, but if you can just talk it through in your head, it is actually quite simple. So, a molecular view of exothermic reactions. Exothermic reactions give off thermal energy, causing the temperature of the surroundings to rise. Where does that energy come from? It comes from some of the chemical potential energy that's stored in the reactants being changed into kinetic energy that's released in the form of heat. So when a chemical reaction occurs, bonds are broken and new bonds form. It takes energy to break a bond. When a bond forms, energy is released. So what happens in an exothermic reaction is that the products have less chemical energy than the reactants did. That energy difference is what got released into the surroundings as heat. An endothermic reaction is the opposite. Here, an endothermic reaction causes the temperature of the surroundings to go down because it's sucking thermal energy out of the surroundings. Where does the thermal energy go? It goes into the chemicals, the reactants. It gets stored as chemical energy in the products. So the products have more chemical energy than the reactants did. Again, we've got existing bonds being broken, new bonds being made. Here, the bonds that are being broken, that requires more energy than what is released when the new bonds form. So, any questions? So, enthalpy of reaction, that's that H that we've been talking about. Enthalpy changed for a chemical reaction. We call that delta H with a subscript RXN. That's our abbreviation for reaction. The enthalpy of reaction or the heat of reaction. This is an extensive property. It does depend on how much stuff there is, right? So if you imagine burning a teaspoon of gasoline or 5 gallons of gasoline, which one is going to release more energy into the surroundings? The 5 gallons, right? More substance, more energy. So the heat of reaction depends on how much stuff there is. So by convention, when we express the heat of reaction, we do it in relation to the chemical equation. So here's the chemical equation for the combustion of propane. And we say delta H for this reaction is negative 2044 kilojoules. Well, for how much stuff? For the molar amounts in this balanced chemical equation. So this would be for 1 mole of propane burning. This is the amount of energy that would be released. This doesn't say per mole of propane, but we understand that this refers to 1 mole of this, 5 moles of oxygen, 3 moles of carbon dioxide, 4 moles of water. Okay, so it's this to any one of these factors in here, and this is a great little conversion factor. So if we know how many moles of stuff, we can tell how much energy was absorbed or released. And so you just take this and you can relate it to any one of those. You don't have to go through all of them. You just pick the one you need, and the number in front of it is how many moles. So ammonia reacts with oxygen according to this equation. So we have a balanced chemical equation, and we've got delta H. So the heat of reaction here is negative, meaning this is an exothermic reaction. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So ammonia is reacting 155 grams. How much energy is going to be transferred in that? So this is done with dimensional analysis, and it's similar to stoichiometry, which was grams to moles to moles to grams. Remember that? My starting value is a mass, so I'm going to start with moles, And then I'm going to go to moles of ammonia. Bless you. But I'm trying to find kilojoules. And kilojoules here, 906 kilojoules are released for every 4 moles of ammonia. I don't actually have to go from moles of one thing to moles of another. I just need to get moles of the thing I know anything about, and then I can go directly. So I can cut both of those things off and just go directly to kilojoules. So 155 grams of ammonia. I want to go to moles of ammonia, and then to kilojoules. I'm going to put the units in the denominators to make them cancel out. We got moles of ammonia. And I can move from grams of ammonia, end up at kilojoules of energy. Grams to moles, that's the molar mass. I'll just save you some time. 17.034 grams is 1 mole of ammonia. Kilojoules per mole, that's the delta H. So delta H is negative 906 kilojoules for 4 moles of ammonia. So 4 moles of ammonia, specified here, will give me 906 kilojoules of energy. Any questions? So then I got my calculator, 155 divided by 17.034 times negative 906 divided by 4. And this gives me a negative number, negative 2061.0, and the unit there is kilojoules. So if I round that for a correct number of significant figures, that's 2060 kilojoules of energy. Energy, heat of reaction, these things can be negative because we're looking at the direction of a change, right? Is there really such a thing as negative $20? Not intrinsically, right? You say, well, maybe if you destroyed a $20 bill, that would be negative $20. But we frequently talk about negative 20. I mean, you go to the ATM machine and you get a $20 bill, and then on your bank statement it says minus 20 later, right? Because that's talking about a transfer, right? So here, energy is being transferred. It can be positive or negative. Any questions?